to Lucas's tutorial to the demo, but sorry, to the agenda. So people should refresh there in about 30 seconds or so. But okay, with that, go ahead, Lucas.
Yeah, thanks a lot, Matthew. And just to say, remind people that we're asking questions on Slido, and if you open the chat in Zoom, you will get the link there, in case you forgot. Right, sorry for the interruptions, Lucas, off you go.
That's fine. Okay, yeah, so I was asked to give a little bit of an introduction to automatic differentiation, and so I also tried to put it into a very long notebook, and so I'm not sure about the timing, but let's try to get through this. Okay, so you might have heard about automatic differentiation. It's basically a way to get derivatives of computer programs. And so this is a pretty old idea, but it's been kind of come to the forefront with the rise of machine learning, and especially gradient-based methods in machine learning. So everybody who's ever trained a neural network has probably trained it with gradient descent. And so the gradient word is the key word there. So if you want to train a neural network, you need to be able to compute the gradients with respect of the loss with respect to the weights of the neural network efficiently, so that you can minimize basically your loss function and find the weight configuration of the neural network that is kind of optimal. And so, okay, but so machine learning is not the only kind of situation where you need gradients. Obviously, you know, like standard statistical analysis and high energy physics, likelihood fitting, hypothesis testing also require gradients, and uncertainty propagation is kind of multiplication of Jacobians, which are also gradients. So gradients kind of come up a lot, and so a lot of what we do essentially involves optimization, like cut optimization and all these things. And so every type of optimization requires gradients. So automatic differentiation is a very specific way to compute derivatives. But before we delve into that, we might want to kind of review what other approaches we could do. So the one that is kind of probably best known is the finite differences approach. So we all know from our kind of pre-calculus class, you know, how to approximate gradients. So you just basically take, you know, you evaluate the function at two nearby points, and then you divide through the distance of the points that they're apart, and then basically the ratio of the differences is a approximation of the gradients. And so that becomes a good approximation of x, or this difference between the point or spacing is sufficiently small. And so we can try to do this. So I have like a small black box function. So it's not black box here because you kind of see what it is. It's x cubed, right? And then the true gradient function, of course, we know is 3x squared. And so we can kind of do these finite difference gradients in a very simple way. And so NumPy has this gradient function where it basically computes finite difference gradients, and we can compare it to the true gradients. And so what we see here is if the spacing is pretty coarse, the approximation can become bad at certain points. And so this is the x cubed at coarse spacing, and then you have the true gradient in green, and then you have the finite difference gradients in orange. And but if you make the, so you know, maybe that's not the most accurate gradient, but if you make the spacing a lot finer, then the approximation becomes better. So that kind of gives you kind of like a you know, like a feel of what the situation is here. So the pro of this is basically that the difference gradients, the only thing that you need to do is you need to be able to evaluate your program that you want to kind of take the gradient with respect to, and nothing else is needed. There's no framework needed. You just need to be able to kind of compute the function. And but then the drawback is, of course, that it's inaccurate unless you do a lot of evaluations. And then if, so this is gradient in one direction, right? So you have df dx. If you have, imagine you have a multivariate function where you have a function that is dependent on a lot of parameters. every time you want to go into a different direction and compute the gradient, that is another set of 2 evaluations. So it's scaled totally with dimensions. And if you recall, neural networks can have the number of weights in a neural network can easily reach millions. And so obviously, if you wanted to train a neural network with finite difference gradients, you'll not get very far. And so finite difference is very robust, but it also has a lot of drawbacks. And then the other thing that you might be thinking of is symbolic differentiation. So in a computer algebra system, so the main one here is Mathematica, or in the Python world, it's SymPy. And here you can basically manipulate kind of expressions, and then the computer algebra system knows about the differentiation rules and can apply those in a pretty rote way, and then just produce expressions that correspond to the exact gradient. So that's much better. So let's try that. So I'm going to import SymPy here. And so you can basically, you still have these functions. So you have like x cubed and then 3x. So that's a true derivative, 3x squared. And so if you apply this function to like a symbol, so this is not anymore like a specific value like a normal Python, but it's just like a symbolic placeholder. And basically what you get out here, if you pass this through the function, you get like a new expression, a new symbolic expression, which gives you x cubed. And then this is something that you can then evaluate. So you can use this lambdify to kind of evaluate the function. So that's nice. But the real kind of neat thing is that you can differentiate the symbolic function using a computer algebra system. And then you can basically get the symbolic derivative. And so you can see here, okay, I differentiated the function and I get this exact gradient of the function, which is 3x squared. And then I can evaluate that. And so if you kind of compare this to the finite differences situation, this is now much better. So you can kind of compare here. We have the same comparison with a pretty coarse grid. And again, the green is the symbolic derivative, and the orange would be the true derivative, and blue is the normal function. And then you can see, okay, you can hardly make out any difference between a true derivative and the symbolic derivative. The reason is because the computer algebra system applied the differentiation rules correctly and then just came up with the exact real function. And then that's basically correct, or the true derivative up to machine precision. And it doesn't really matter how much you evaluate or where you evaluate it. It's just always 100% correct. So even if you go to a super coarse grid, I mean, the function will not look nice, but the gradient values will be exactly right. Okay, so that's symbolic derivatives. Okay, then function composition is also easy. So if you wanted to do kind of the composition of two functions that operate on a symbolic value, you can basically get this composition. So here it's like cosine of x squared. And then the computer algebra system is also smart enough to do the chain rule, and then you can do this. Okay, so great. So you might think, okay, problem solved. So we get very exact gradients. And what's the issue? So why do we need anything else? So the first kind of drawback is that you need to implement whatever program you're intending to run, you need to implement that in the language of the computer algebra system. And so you all know our reconstruction and analysis software is not implemented in a computer algebra system, but it's like a bunch of C++ or C or Fortran or Python code. And so usually it's not in the kind of general purpose language, but okay. So I use SymPy here, and like the selling point of SymPy, unlike Mathematica, which is a pretty hermetically closed world unto itself, the appeal of SymPy is that it kind of uses native Python language constructs to kind of overload their meaning, and you can basically get away with programs that look very similar, no matter if you use the symbolic version or the kind of non-symbolic version. So you might only kind of differentiate itself by using import statement. Oops, what's going on? Right, so you like this section here, like F1 and F2, it's exactly the same source code. The only difference is that it's kind of the import for the cosine function is different. And then so that's already nice. But the issue is, of course, that not all our functions are so super simple. And so one thing that can happen is something that is called expression swell, which kind of happens if you have kind of standard programming practices like recursion or like looping constructs and whatever. So we have a pretty, let's take a look at a pretty simple function, which is x squared plus 3x plus 4. And so we then, so that's pretty banal. And then we have like a function that just loops six times and then kind of updates the value itself kind of onto itself. So you kind of replace the x value with this quadratic map, and then you run this 6 times. And then if you look at kind of what the expression looks like, it's kind of horrible. So I mean, the notebook doesn't really do it justice because you need to scroll a bit as well. And so it's like a super complicated expression, and basically everything gets unrolled. So the notation here is super tidy and like well structured, but then like it kind of explodes into this horrible mess. And so that's because like once you run the symbolic the function on the symbolic value, everything gets unrolled. So that even gets worse if you try to differentiate this. So if you differentiate this, okay, this is kind of what it looks like, and again it looks even more horrible. And so you have like all these expressions, and then like you have to scroll a bit, or okay, and then you have a lot of these expressions. And so so if we would now just go ahead, so the way that we would evaluate it kind of naively is that, so every time there's, so this is a function of a single variable, so there's like a bunch of x's here. And so if you would just evaluate it simply, we would actually end up computing a lot of things multiple times. So you might notice that like this x squared plus 3x plus 4 is kind of present at a lot of different locations. So you have this here, right? And so that is basically, so why does this happen? So this basically happens because of this kind of looping construct. So it's kind of like a remnant of the source code structure, but like SymPy or the computer algebra system doesn't really know anything about this kind of original structure of the program. It just kind of unrolls everything and then kind of flattens it out into all a single everything, until everything is a single expression. And then if you would just kind of replace x with a numeric value and then evaluate everything, we would end up kind of computing, for example, x squared plus 3x plus 4, a bunch of times, and that's super wasteful. And so it's not super efficient. And so one thing that modern computer algebra systems can do is that they can actually recover some of these common sub-expressions. And so you can, in SymPy, you can call this common sub-expression function and then kind of try to recover some of the structure. And lo and behold, we see this 3x plus x plus 4, that we've seen above. So this kind of, recovers some of the structure, and then this allows you to be a little bit more efficient in how you evaluate these things. But it's not automatic because it doesn't really know anything about the structure of the original program. And then you have to do a lot of work to kind of backtrack and kind of regain the structure, which is a little bit tedious. And then so it's not as automatic, and it really depends on what this algorithm is to find these common sub-expressions. And so that's the problem with,
You've got one request in the chat to increase your Zoom, the text size.
Yeah, sure.
Right.
Oops. Does this work better? Does this work better?
That looks better to me.
Well, that's
okay. Okay, so this is kind of one annoyance with computer algebra systems, but okay, maybe you might learn to deal with that. But another kind of basic problem is that, okay, a lot of our functions that we tend to want to evaluate, actually like our programs, they tend to have control flow statements. So they have like if-else constructs and looping statements, and break out from a loop and continue, and maybe we even have go-tos. And so the computer algebra systems can't really kind of deal with this in a graceful way. So let's have a like pretty benign function that is kind of branched in two ways. So like if x is greater than 2, it's x squared, and then otherwise it's x cubed. So this is a perfectly respectable function, which is very much differentiable almost everywhere, except for a single point. You might hope to be able to differentiate this, but if you try to do this in SymPy, like you get an error because SymPy cannot really handle this branching statement in the way that it's written here. And so because it says, okay, I cannot determine the truth value of this construct. And so it can't really do this, but if we go back to the original function, this is what it looks like. It's very smooth. It's a pretty nice function actually, right? But only that it has like this one point where it's kind of, it doesn't have a well-defined derivative, but everywhere else it's has a derivative. And so if we went back to the finite differences way, which is kind of the dumb version of computing derivatives, but the robust one, the gradients compute just fine. So so this is like on the left-hand side, you have like this section, which is x cubed, and on the right-hand side, you have the section, which is x squared, right? And then here you get, okay, in the x cubed section, it's kind of a quadratic derivative, and then in the from the quadratic original function, it becomes a linear derivative. So as you would expect, and then as you would expect also close to this boundary, okay, it becomes undefined, but most of the time you will not hit exactly the points where it's undefined, and everywhere else you have a pretty well-defined derivative. Okay, so let's go on. So just to recap, we have two methods that we might think of first if we wanted to compute derivatives. We have the symbolic differentiation and the finite differences one, and the finite differences one is a little bit brute force and not efficient, and the symbolic differentiation alleviates some of that. So you have exact gradients, and but kind of depends, or it restricts a little bit of what you can actually compute, and you need to implement that in a computer algebra system, and computer algebra systems are not easily available in all like programming languages. So Python is one exception where you have a computer algebra system that tries to like overload the natural construct of the language to kind of co-opt as a computer algebra system, but for them in Mathematica, it's a completely different programming language, and there are no computer algebra systems, maybe like in Golang or Java and whatever. And so, and then additionally, you cannot really handle control flow structures in a super easy way. Okay, so this is the situation what we have, and so both are not super satisfying because they both have drawbacks. So like what we would really want is like to have a third approach, which is one that is exact, efficient, can handle arbitrary programs, and then it's easy to implement in many languages. And this third approach is automatic differentiation. So before I'm going to talk about automatic differentiation, I want to make a short detour into kind of linear transformations, because in the end, that's what derivatives are. And so if you just kind of consider to have like a linear transformation, which is kind of, you have some, you map from some source space, which is m-dimensional, into some target space, which is n-dimensional. And then you have some operator, some linear operator here. So this linear operator can be described as a kind of rectangular matrix, right? And then, so how do you compute this program? So you might imagine you have a computer program, which is basically a linear transformation, and then how do you compute this? So one way to do it is to kind of go into the linear transformation and figure out kind of what exactly the coefficients are for every kind of component in the source vector to map to the target vector, and then you kind of can actually literally construct this matrix, right? And then you do like a full matrix computation, and then you have a very kind of generic way to evaluate any type of linear transformation by just using the matrix multiplication function of any language that you want. And so in this case, it's NumPy. Okay, you have some matrix that you somehow derive, and then you have some input vector, and then you can compute the result. So that's nice, except when the matrix becomes very large. And again, consider that neural networks can be like 1 million dimensional. And so obviously then a lot of these connections might be kind of actually not active. And so if a lot of these matrix elements are 0, might actually be wasteful to store the full matrix, which is n squared elements. And so you might actually use a sparse matrix, and then so that stores only the non-zero elements, and then has some kind of lookup table to say where in the matrix these non-zero elements are situated, and then you can basically do a sparse matrix multiply, take the sparse matrix, and then compute the result. And this is still super generic, so you can just put in any sparse matrix, and then you get the result. And so in this case, the program is actually like a data structure. So in both cases, the matrix is like a data structure that is stored somewhere separate from the algorithm to evaluate it. And then the third way is to have matrix-free computations. This is basically where we kind of hard code the linear transformation. This is usually the case in which we have most of our programs. So even if we have programs where, like in principle, we could have the some kind of coefficients, oftentimes we kind of actually write it out as code. And then the only thing that we don't really have access to the individual matrix elements, but we can only compute these matrix vector products where you put in the vector and then kind of implicitly does the linear transformation and then outputs an output vector. Okay, so if you don't have really access to these matrix elements, the question is, can we recover them? And then the answer is yes. So if you kind of want to figure out like what this matrix is, you can basically just feed this machine that just takes vectors and spits out other vectors, like kind of well-crafted input vectors, and then with these well-crafted input vectors, you can actually kind of recover the full matrix. So if you would put in like the different basis vectors, you can actually kind of reconstruct the various columns of the matrix. And then once you have the various columns, so you need to basically run this machine 3 times, and then you get the full matrix. And so that's kind of nice, because basically we can recover the full linear transformation by just running this kind of opaque black box machine, which is computer code, a bunch of times, and then we can get the full kind of matrix. So this is a matrix and vectors, and this is called like a matrix vector product, obviously. But actually, it turns out you can actually also go the other way. So instead of, so you notice this is doing one column at a time, and then it gets assembled into this full matrix. But you can also go one row at a time, and this is because you can basically kind of feed in the basis vectors from the other side of the matrix, and then if you run the vector matrix product instead of the matrix vector product, you can recover one row at a time. And so in this case, we need to run the kind of the machine twice to get the 2 rows. And then we also recover the full matrix. And so this is a matrix vector product. And basically what is here is, so this is basically computer code that implements this vector matrix product accordingly, the same way that this code up here implemented the matrix vector product. And so in this case, so you'll notice what kind of happened. And so in this case, we needed to run the machine 3 times to get the full matrix, because it was column at a time. And up down here, we needed to run it only twice because it was row at a time. So depending on what the shape of this matrix is, you might want to either use this matrix vector product version or this vector matrix product version. And but in any case, you can recover the same matrix. So you can see up here, so you have this matrix here, if we compute it one way, and then we have the other matrix here, which we compute a different way, and this is exactly the same result, and doesn't really matter. It's just a matter of computation efficiency, which direction kind of requires the fewer evaluations. And so if you recap this, basically, so we kind of have some kind of linear transformation that is characterized maybe implicitly by such a matrix, but even if we can only evaluate the program at different inputs, we can still recover the full matrix sooner or later by kind of feeding in specially constructed inputs. And yeah, if you go to function compositions, the linear compositions of linear functions are still linear functions. And so it's, the idea is still the same, that you kind of feed in specially constructed input vectors, but then instead of going through one matrix, they go through a series of matrices. And so if you feed it in from the right hand side, you basically run forward. So you kind of evaluate these matrices one at a time. And then so you kind of eat away on this chain of matrices. And then so this runs forward. And then in the end, you get your result. So this is a column in your kind of linear transformation that you want to recover. Or you go the other way around, and then you eat away from the other side, which so you feed in like this row vector, and then you kind of do these matrix multiplications. And then so this is going backwards. And so this is propagating, so to say, a computation into the forward direction. This is, so to say, back propagating this input vector through this composition of functions, and then you arrive at your row of the kind of linear transformation that you're interested in. Okay, so this is all well and nice, but of course not all our kind of computations are kind of just matrices that we're multiplying together. And so instead of, so you can also kind of view kind of linear transformation, so you can view it as a series of matrix multiplication, but you can also view it as a series of graphs. So if you have kind of a map that goes from a 3-dimensional to a 4-dimensional to a 3-dimensional to a 2-dimensional space, so it's either like a set of matrices here, or you can also construct it as a directed acyclic graph like here. And then every edge here basically corresponds to one of these matrix elements. And so if you write down basically what the values are of the intermediate values, if you kind of start evaluating these matrix multiplications, this is kind of the normal matrix multiplication formula. So you have yi is iik xk. So you have so you do the series of scalar products, or if you go like multiply from the other side, you have the vector here and the matrix here, and so the order is reversed, but you still sum over the indices that are common. And so, but you can also kind of translate this to this graph language, where so either if you go the matrix vector product route, you kind of sum over all the input values in the graph. So if you want to compute this, you need to sum over all of the incoming edges. Or if you want to go the other way around and compute the vector matrix product, you go the other way around. So you, in order to compute this, you need to compute all the values from the other side, which are kind of along the outgoing edges. And so the nice thing here is basically that this allows you to kind of go into a more generic picture where you have a computational graph, which is linear, but kind of has kind of a more complex structure. And so this is a computational graph as you would normally kind of see it in if you run some kind of series of statements in your computer program, right? So you have like some value that might get computed from other incoming values, and then that might become the input to the next value, and so on. And then at some point, your computer program is finished. Okay, so so this is just to say that you can basically do the same thing. So if you basically take the same idea as the matrix vector product and the vector matrix product, but kind of compute it using these formulas where it's more kind of in the language of edges of directed acyclic graph, you can still kind of in spirit do like this matrix multiplication, even though you're not actually using, let's say, NumPy matrix multiply, and you still recover the same matrices in the same way that we recovered them before. Okay, so this is this detour into linear transformation. So let's talk about derivatives. And so you might wonder, well, okay, why did I spend so much time to talk about linear transformation? The reason is because this is basically the entire trick of the automatic differentiation. So even if our normal functions, so obviously not all our functions are linear functions, but a lot of our functions are non-linear in very complicated ways. But the entire point of derivatives is that it's a linear approximation of that function. And so that is always linear. So learning above about linear transformation was kind of set up for this. And so, and then crucially, the composition or the derivative of a composition of nonlinear functions is still the composition of kind of linear derivatives. So this is nothing but the chain rule. And so if you have a complex series of kind of compositions, function compositions, then in the end, the only thing that you need to do is to multiply together the Jacobians. And so you now, if you have like the series of Jacobians, you can then basically do the same trick. So you have like the series of matrices, but we don't know exactly what this matrix is. And so we're exactly in the situation that I explained above. So we have some kind of matrix that we only know kind of implicitly. And so we want to kind of find out what this matrix is, and then we can do the same kind of trick that we did before. So before I called it matrix vector product and vector matrix product, but if the matrix in question is a Jacobian matrix, people usually use these terms Jacobian vector products and vector Jacobian products. And this is basically, so there's really nothing fancy. So sometimes I think in the machine learning literature, it's to my eyes kind of presented in a bit convoluted way, but it basically only is the decision, okay, do you start multiplying these matrices together from the right-hand side, or do you start multiplying these together from the left-hand side? And then you basically get these various, so either the Jacobian vector product or vector Jacobian product. And then this is exactly what is meant by automatic differentiation. So either in the forward propagation or reverse propagation mode. And so in machine learning, most of the time, it's reverse propagation because so this is the case where the Jacobian is kind of wide, where it's only one row because you have a scalar output, but many inputs, like millions of inputs. And so the efficient way to derive this is to use this reverse mode or back propagation algorithm, which basically computes a row at a time. And so since the entire Jacobian only has one row, you're basically done. Okay, so let's try to work this out in a super simple example. And so let's say you have like this kind of computational graph where you have put values and then some kind of intermediate output value. And then you kind of have a third value, which kind of takes this input, this intermediate variable and one of the input variables. So you can either kind of compute this as a kind of a matrix, this matrix picture, which kind of requires you to add some kind of dummy edge just in order to not jump over the graph in a way, because in a matrix multiplication, you only kind of can have edges across adjacent layers. Or you can also represent this just in this directed acyclic graph. And so you basically only compute this product of two Jacobians, and this is basically the derivatives. And so, so in the simple example, you of course know the full Jacobian matrices, but recall the automatic differentiation is relevant if you don't really have access to this full Jacobian yet, and you just have a machine through which you can push values and you get some values out. And so we can try to do this by doing the forward propagation mode. So here, basically, the forward propagation mode is pushing kind of prepared input vectors through these Jacobians. And then you get the derivatives, and in this case, you need to evaluate it twice. And then you do a bunch of math, which is basically here for your offline viewing. But in the end, what you get is you get the full derivatives by doing this twice, right? And so this is how you get the derivatives by following this computational graph. And in the backward propagation mode, it's similar. So in the backward propagation mode, it's basically this vector matrix version of it, where instead of kind of going from kind of evaluating a node by kind of taking on values from its parents and pushing it through the graph, you go the other way around, where you evaluate the node and but then pick up values from downstream of the node from its children and then propagate it upwards. And so you kind of push a vector from the left-hand side on this through these two Jacobians, and then you get your matrix multiplication. And then so if you do this carefully, by basically taking on these edges that are in this computational graph, you arrive at an expression like this. And so the nice thing here is that since you only have a one-dimensional output, so it's the entire Jacobian is one row. And so again, so you just need to do this this operation of pushing a value through these Jacobians once, and then you get the entire, all of the gradients. And so this is the case, again, in machine learning, where you have a scalar output, which is the loss function, and then you have millions of weights, and you still want the gradients with respect to all the weights, but all you need to do is to just basically take this computational graph and traverse it backwards once, and then you get basically all the gradients for free. Okay, so let's kind of look at...
time is running on a wee bit, but I suggest that you take 5 minutes more and then maybe try and reach the conclusion, and then we can take a couple of questions.
Yeah.
Thanks.
Yeah, that sounds good. Yeah, so basically, so I don't have that much left. So it's basically, okay, I'm taking the same graph structure here, which is basically, okay, you have these two input values and an intermediate value and the output value, but I just kind of give it life by having like an actual mathematical operation. So this intermediate value is the product of the two input values, and then that gets added to one of these input values again, and then that's the final output value. And so the idea here is that you can have Python code that just runs this function, and then that's great. So you get some function result out of it. And so if you wanted to take a derivative, so what we've learned is basically that we need to create equivalent functions for every operation that we want to do. So in this case, we have two operations. So we have a multiplication and a summation, and we need to somehow implement kind of helper functions that implement this matrix multiplication. And so this is the case here. So if you want to take kind of differentials from your inputs and push them forward to the differential of the outputs in the multiplication, this ends up being the chain rule. So if you want to get dy given x1 and dx2, you get x1 times dx2 plus x2 times dx1. So you have this familiar chain rule of a multiplication, and then you kind of push values through this Jacobian vector product. So this is this JVP. And then for the sum, it's even easier. So so here it's basically the differential from the summation, basically just the sum of the differentials. So this is also just the differentiation rules. So but basically, in order to kind of make this function differentiable, you need to kind of for every operation implement a function that kind of applies this differentiation rule. And in the end, then the kind of function has this same structure where you basically have an input and an output, but now it's kind of expanded to have kind of this tangent value and this tangent output. And but the structure of the program looks very much the same. And so that's one of the nice things about automated differentiation. So you might recall in the symbolic differentiation, the structure was completely lost of the program, and then meant that we had a hard time kind of figuring out what intermediate values we could compute ahead of time and not kind of repeat ourselves. And in this way, if you kind of construct your derivative kind of code like this, it's kind of automatic and keeps the structure. And okay, I'm not going to go through this in detail, but this is now kind of the same thing, but in the other direction, which is this backward propagation kind of picture. And so here it's a little bit different. And so basically here it's, so you still run your normal function forward and you know, taking your multiplication and your sum. But then you kind of, once you've run through your function, you kind of know what the computational graph is, and then you can run it backwards. And then, so you can run these vector Jacobian products backwards, and then kind of you get both of these gradients at one time. And so this is kind of the usual case that is happening in neural networks. So you evaluate your network and then prepare to evaluate the gradients, and then run this backward propagation step. And okay, so this is basically, yeah, so just to recap, basically we have these two ways to compute these derivatives. So it's not, so this is just a very peculiar way to kind of structure your derivative computation. And so you have these two modes, the forward mode differentiation and the backward mode differentiation. And basically, whoops, where am I? Basically, this allows you to kind of reconstruct the full Jacobian of your operation, you know, in a very efficient and automated way. And kind of it circumvents a lot of these issues that symbolic differentiation has. And so what we gain is basically we get exact derivatives, and the complexity of the derivation computation is exactly the same order as the complexity of the original program. So you saw the structure of the program is still the same, even if you do the derivatives, just that you do kind of for every operation that you do one additional operation. So you basically spend twice the time. And oftentimes only a single pass through this program is necessary. So you basically, you know, can get the derivatives of a program in a very efficient way. And then it can kind of handle arbitrary control flows. And this is something, obviously you will not do this by hand, but it's something a computer or a programmer can do very quickly to kind of implement a library. And so this means that it's easy to make this available in a different programming language. And in fact, it is available in different programming languages. Okay, so obviously, okay, so here so this was more kind of educational in order to kind of show what's under the hood in a differentiation system, but obviously you don't really want to implement this yourself, and you might wonder, okay, aren't there libraries for this? And so the entire point is that, yeah, there are a lot of libraries, and there are a lot of libraries in many languages. So this is a table from a paper on where you have all of these different automatic differentiation libraries, and you can see, like, you have Scheme, you have Python, and you have multiple ones in each language. You have MATLAB, Julia, Haskell, and you know, like all kinds of languages. And so this kind of shows that this is much easier to implement than like a full computer algebra system where you want to do symbolic manipulation, but it's enough to kind of get derivatives out in a very efficient way. And so since this is kind of PyHEP, I did want to focus on Python. And so in Python, you might know all of these machine learning libraries, and at the core, what they are basically kind of automatic differentiation libraries. And so they all are able to kind of run the more or less run-of-the-mill Python program and then give you derivatives for this. And so just to kind of show this, so you can have like a function which is kind of x squared, and so we import JAX, and you have your kind of x squared function, which is like a standard Python code, right? And then you have like all the NumPy functionality. So JAX as a library kind of implements all like a drop-in replacement for NumPy. So you can, any type of array calculation, you can do now in a way that is differentiable. So you can kind of add arrays, you can multiply arrays, you can take the logarithm, you can take the exponent. And but if you use these JAXified versions of NumPy, all of this becomes differentiable. And so just to show that this is kind of actually doing, you know, the gradients, you can have like x cubed, and then you can have not only the gradient, you can have like second order gradients, third order gradients, fourth order gradients, any type of order that you want. And it still kind of gives you the exact result. And this is very different to what you would get with finite differences. So if you want to kind of evaluate this, so this is x cubed. And if you just kind of want to evaluate in a broadcasted way, this will fail intentionally, but you can kind of teach JAX to broadcast this correctly, and then you can basically get, so you have x cubed, and then you have kind of x squared, and your linear, you know, third derivative, and then the third derivative, which is then a constant, right? And so, but you can, so everything is exact as you see, so you can get any type of order of differentiation correctly. And you can also do control flow. So this is the same example that we had before, which is x cubed and x squared. And then so here it's again like a comparison of autodiff and the finite difference is one. And so here you can see, you know, what you gain. So the black one is the true derivative, and then so the autodiff one is all exactly on point. And then the finite difference is really starts to become bad, especially because it kind of depends on exactly where you are in your derivative with respect to this discontinuity, and becomes very sensitive. And so this becomes even worse if you go to like second order derivative. So where this is a parabola, this is a line. The next, if you differentiate that again, you get like a line and a constant value. And then you see that the finite difference is one just really has nothing to do anymore with the true derivative. And so, but if you use automatic differentiation, it stays quite exact. And so you can basically then you use these automatic differentiation libraries to get any type of in any order of derivation. You can get Hessians and all kinds of different derivatives. Okay, I'm going to skip this, which is operations, which kind of discusses things where, you know, we have kind of constructs inside of our code which are not per se differentiable. So I'll leave this out for the sake of time, but I did want to quickly maybe segue into Nathan's talk, where it's talking about how we can use this in high energy physics. And so as I said, so we can of course use automatic differentiation for neural networks, but it's kind of limiting artificially of where we can use this tool, because we need derivatives and minimization, optimization, and many other respects in high energy physics too. And so one kind of marquee example is statistical analysis, where we want to do maximum likelihood fits, where it's you know, minimizing the log likelihood or negative log likelihood. And so there obviously knowing, and that's such a minimization procedure, knowing the exact gradients is super useful. And so PyHEP is basically one tool that we've written in order to kind of make use of these automatic and machine precision exact gradients in order to help the statistical analysis or minimization of the log likelihood. And so kind of see that we've basically implemented you know, some kind of statistical model and using JAX or any other machine learning framework that is available in Python. And then we can run this maximum likelihood estimate fit. And then this will give us best fit value. And so in this case, okay, it's a very simple best fit value. And but you can kind of see here that basically, so this is the likelihood. So this is the likelihood of two variables. And so this is the full likelihood landscape, and then the best fit value is shown. So it was 1, 1 when we did the maximum likelihood estimate. And so this is the best fit value. And so if you plot the full contour here and on top of the gradients, so you can see that the gradients are all exact. They all kind of point in the right direction. And then having access to these super exact gradients are is actually you know, makes the fit go you know, orders of magnitudes faster than if you use something like Minuit, which in the standard configuration would use finite differences. Okay, so but I'll leave this for Nathan to go through. And so thanks for joining the tutorial. I think it was a little bit too much of material, so I didn't time this perfectly, but I hope it's a good resource to kind of go through this offline and by hand. And so I did want to just finish with this one paper from the like early 90s. So this is not a new idea in certain circles, that you kind of want to make a lot of your workflow differentiable. And so this is from Jürgen Schmidhuber, who kind of invented the LSTM. And so there's like this notion that we can kind of reformulate a lot of our workloads in a differentiable way, and then make use of these kind of automatic optimizations efficiently. And yeah, so I think I'll stop with that.